Hello learners, welcome back to my channel Shraddha's Physics. In this lecture, we will start with the DSC second part, that is the second DSC paper, Nuclear Physics. So in this lecture, we will discuss on the constituents of the nucleus and their properties. Now let us start with our topic, constituents of the nucleus and their properties. So in case of an atom, suppose this is your atom, so it consists of the positive charge, or you can say that this part is called the nucleus, and this nucleus contains proton as well as neutron, and surrounding to this nucleus the electrons are revolving around. So here the electrons are present, okay, and so on. So here the proton carries the positive charge and the neutron having the neutral in nature, neutron having no charge, so it is neutral in nature, and the electron, it carries the negative charge and etc., whatever it may be. So before discovery of the neutron, so what are the hypotheses that are being considered? Today we are going to discuss that. So now let us see the constituents of the nucleus and their properties. So the study of the radioactive disintegration, it indicates that the emission of alpha, beta and gamma particles or the rays to be of nuclear origin, and the study of the artificial radioactivity, it has revealed many other particles like proton, neutron, alpha particles, beta particles, and the cosmic ray study demonstrate the subatomic particles like meson, positron, neutrino, it enter into the constitution of the nucleus in one way or other. So these particles, the positron, neutrino, we are going to discuss that in our particle physics, that is in your unit 4, that is particle physics. We are going to discuss in that part meson, positron, neutron, neutrino, etc. So now the basic thing is that the radioactive disintegration, it indicates the emission of basically the alpha, beta and gamma particles, and this radioactivity, it has revealed the particles like that is the existence of the proton, neutron, etc. at discovered. So now the several theories were put forward about the actual constituents of the nucleus. The prominent among them are the proton-electron hypothesis, and the next one is the proton-neutron hypothesis. So in these two hypotheses, we will see basically the constituent of the nucleus. Okay, so our main aim is to know the constituents of the nucleus, that is the nucleus is made up of what. So now let us see first the proton-electron hypothesis. So this proton-electron hypothesis actually comes before the discovery of the neutron, or you may say that before the Chadwick experiment. So this is before the discovery of the neutrons by the Chadwick. It was assumed that the nucleus is made up of protons and electrons. That is, it is being considered that some protons as well as some electrons, they are consisting of the nucleus, that is the proton and electrons, and some of the electrons also, they lies at the outer part of this nucleus, so that this total atom, it is being in neutral in nature. So because of the why it has been considered that the nucleus is made up of protons as well as electrons, because some radioactive nuclei emit beta rays during beta decay, and beta rays were found to be the fast moving electrons. Since the emission comes from the nucleus and the beta decay or the beta rays, these are the fast moving electrons. So basically it has been considered that this nucleus consists of the protons as well as the electrons. And next, the slight change from the whole number explained by the two or more isotopes. The nuclei of hydrogen atom has a positive charge whose magnitude is equal to the electron, and that was known as the proton. So because of this reason, we considered that, or we can say that this proton-electron hypothesis was considered that the nucleus is made up of protons as well as electrons. But this theory was rejected because of the following problems. That is, what are the failure of this hypothesis? That is, according to the de Broglie and the Heisenberg uncertainty principle, if an electron is to exist inside the nucleus, it should possesses the energy ranging from 20 mega electron volt to 200 mega electron volt. But the energy of the electron during this beta decay is 2 to 3 MeV. That it means that according to de Broglie theory and the Heisenberg uncertainty principle, if an electron will exist inside this nucleus, then it should possess some amount of energy, that is from 20 MeV to 200 MeV mega electron volt. But in the actual case, or we can say that from the beta decay experiment, the electron possesses the energy of 2 to 3 mega electron volt. So if I'll consider the size of the nucleus of the diameter d equal to suppose 10 power minus 14 meter, if we'll consider the diameter of the nucleus is 10 power minus 14 meter. So the uncertainty principle says that this change in position with the change in the linear momentum, it should be greater or equal to h cut by 2. And this h cut is nothing but h by 2 pi. This h cut equal to h cut, or it may be pronounced as h bar, that is equal to h by 2 pi, where this h is your Planck's constant. And this delta x is nothing but the diameter, because if you will consider the size of the nucleus and this one is your diameter, so the change in position, this one is your delta x, and this is equal to 10 power minus 14 meter. And from that relation, if we will consider this is near equal to h cut by 2, so this delta px will be equal to h by 4 pi, that is, since h cut is your h by 2 pi, so this will be h by 4 pi into 1 by delta x. Okay, so now if I will consider the linear momentum of the electron is p, then we can consider this p equal to delta px. This p equal to delta px, and again in place of delta px, if I write p, then that will be equal to h by 4 pi into 1 by delta x. Okay, now according to the theory of relativity, the energy of the electron, it should be equal to m naught square c power 4 plus p square c square whole root over, where the c is the velocity of the light and m naught is the rest mass of the electron and p denotes the linear momentum. And also we know that this m0 square c power 4, it is very less than the p square c square. So we can say that this m0 square c power 4, it can be neglected as compared to this. Now we can write, if I will neglect this term, that is tends to 0, so then this E will be equal to p square c square root over, or simply it can be written as E equal to p into c. So we concluded that E equal to pc. And again, if I put the value of p equal to this much here, so this will be equal to h by 4 pi into 1 by delta x into c. Okay, or this is your sc by 4 pi into 1 by delta x. Now if I put the value of this Planck's constant, that is 6.62 into 10 power minus 34 into the velocity of light is 3 into 10 power 8 meter per second, divided by 4 into pi is 3.14 into this delta x, we have considered the diameter of the nucleus, that is 10 power minus 14 meter. So simply substituting that value, we will get after calculation, that is 10 mega electron volt. So it means that if the electron exists inside the nucleus, then the energy of the electron, it must be of the order of this 10 MeV. Okay, but actually in the real case, it is just about 2 to 3 mega electron volt as seen in the beta decay of the emitted electron. So this is not possible for the electron to lie inside the nucleus, since the energy should be of the order of 10 mega electron volt, because from the mathematical calculation also, if you can check, this is your 10 MeV. So this is not possible for the electron to occupy or to lie inside the nucleus. The next one is the observed values of the nucleus spin or the angular momentum of the nuclei. It rule out the possibility of the existence of the electron inside the nucleus. So these are some reasons why the electrons doesn't lies inside the nucleus. So and again, the experimentally the values of the magnetic moments of the nuclei, it is much smaller than the magnetic moment of the electron. So electron cannot exist inside the nucleus. So what are the basic reasons? Because the first reason is because of this energy. The experimental result energy, this is of the higher order as compared to the original, that is your 2 to 3 mega electron volt it should have. But in the actual case, you can see this is your 10 mega electron volt. So this is not possible for the electron to lie inside the nucleus. And the second reason is because of its spin. And the next reason is because of its magnetic moment. The magnetic moment of the nuclei is very small than the magnetic moment of the electron. so electron cannot exist inside the nucleus. So basically we can say that this proton electron theory or this proton electron hypothesis failed, and that after Chadwick come and he explained the existence of the neutron inside the nucleus. Now let us see the proton neutron hypothesis. The proton electron theory, it was rejected due to the properties of the free electrons. And according to the Rutherford alpha scattering experiment from the gold thin foil, the scattering of the alpha particle from the atom, it is due to the positive charge or the proton in the nucleus. And if the electron will exist inside this nucleus, then it might be possible that the alpha particle, it is being captured by the electron, since alpha is the doubly charged. This is your doubly charged helium nucleus. This alpha particle is nothing but this doubly charged helium nucleus. We will discuss on this alpha, beta decay, etc. So this alpha particle is nothing but 2He4, and if it will get bombarded with this gold thin foil, then since it is a doubly charged helium nucleus, so it will get captured for this with this electron. So now this electron will capture this helium or this alpha particle, so which is not possible in actual case or in experimentally. It has been found that some of it is getting deflected, and exactly at the nucleus it is getting 180-degree reflection exactly. So basically we can say that from the alpha particle scattering experiment, we conclude that due to the positive charge there will be the repulsion occurs and the non-existence of the electron inside the nucleus is being proved. Now the Chadwick comes and he discovered neutron when alpha particles is being bombarded on the beryllium. So you can see this is your 4 beryllium 4Be9 with the 2He4, this is your alpha particle. Okay, so this is equal to, this will be equal to 6C12 plus 0N1, this is your neutron, plus some amount of energy, that is suppose Q. And here you can see the neutron is 0N1 equal to the neutron, and it has the mass 1.6748 into 10 power minus 27 kg. And this neutron, it is the neutral particle and not affected by the electric and magnetic fields. Okay, since this neutron is a neutral particles, so it will not deflected or it will not be affected by the presence of the electric and magnetic field, but it has the very high penetrating power. So according to this hypothesis, that is the proton neutron hypothesis, every nucleus, it consists of the protons, that is Z, and the neutrons, that is N, and the sum of this is called, that is sum of the neutrons and the protons, that is called the atomic mass number, that is denoted as 8. So we can write this atomic mass number equal to, or simply mass number will be equal to sum of the proton number plus the neutron number. Now let us consider the diameter of the nucleus is now 10 power minus 40 meter. Now what we are going to discuss here, that is, now we will prove that this nucleus, inside this nucleus the neutrons should be present, so that it should have that much of amount of energy. Now let us consider the diameter of the nucleus is 10 power minus 14 meter. Since the neutron or proton is considered here, we are considering whether it is for the neutron as well as for the proton, it is also true. So the neutron or proton is considered to be present inside the nucleus, then the uncertainty in the position of the proton or neutron, so we can write this delta x will be near equal to 10 power minus 14 meter. This is near about 10 power minus 14 meter. So now according to the uncertainty relation, we can write this delta x into delta px equal to near equal to h cot by 2. H cot or h bar, this is equal to h by 2 pi. Okay. Now the momentum of the proton, if I will consider that is p, that here it may be proton or for the neutron. Okay. This is equal to delta px, and also this will be equal to, if I will put the value of h by 2 pi here, so this is nothing but h by 4 pi. So from this relation delta px will be equal to h by 4 pi into 1 by delta x. Okay. Now if I will put the value of this h, that is 6.62 into 10 power minus 34 divided by 4 into this pi is 3.14 into this delta x equal to 10 power minus 14, then the answer will be, this is your 0.527 into 10 power minus 20 kg meter per second. This is the momentum of the proton. Now the rest mass of the proton or the neutron, we know this mass equal to 1.67 into 10 power minus 27 kg. This is also for the mass of the neutron. Let the velocity of the proton, or you may say that neutron, that is equal to, the linear momentum equal to the mass into velocity. So you can write the velocity will be equal to the linear momentum divided by the mass. So here this is the velocity will be equal to linear momentum divided by the mass. So here the linear momentum we have calculated, that is 0.527 into 10 power minus 20 divided by, this is your 1.67 into 10 power minus 27 kg. Okay. Now this is your 0.527 into 10 power minus 20 divided by 1.67 into 10 power minus 27. If we will cancel this term, and after solving this you will get 3.15 into 10 power 6 meter per second. This is the velocity of the proton or the neutron. Since you can say this is a non-relativistic case, because in case of the relativistic case, so C will be equal to 3 into 10 power 8 meter per second. So it is simply 3.15 into 10 power 6 meter per second. So this one is a non-relativistic case. Now if I calculate the kinetic energy of the proton, then the kinetic energy E will be equal to P square divided by 2 mv. This is proton, or you may say that this is for the neutron. Okay. Then this will be equal to, the linear momentum is equal to 5.27 into, if I write this 5.27, then this will be simply 10 power minus 21. So this will be 5.27 into 10 power minus 21 whole square divided by 2 into mass of the proton is 1.67 into 10 power minus 27. And after solving we will get, this is 52 kilo electron volt. Since emitted proton or the neutron by the nucleus, it can carry energy greater than this 52 kilo electron volt, then we can say that the proton and neutron surely exist inside the nucleus. Okay. So here from the mathematical calculation, this energy is equal to 52 kilo electron volt. So we may conclude that the proton and neutron, it surely exists inside the nucleus. And the next is the magnetic moment of the proton and the neutron. They are of the same order of magnitude and equal to the nuclear magneton, that is this nuclear magneton, this is the unit of the magnetic moment of the nucleus, its value equal to E h cot by 2 mp. Okay. So from this magnetic moment also we can conclude that this proton and neutron, they exist inside the nucleus. And the next one is, since the mass of the neutron is nearly equal to the mass of the proton, so the sum of Z plus N, that is the proton number and the neutron number, it will give the mass number. And the next is the beta decay. It shows that electrons do not exist inside the nucleus. They are produced during the radioactive disintegration. Now you can see that if this neutron will disintegrate, then you will get this is your proton plus this is your electron and this is your antineutrino. This nu bar, this is your antineutrino. This one is your antiparticle. And if this 1p1, that is your proton, will disintegrate, then it will give 0n1, that is the neutron, with your positron, that is plus 1 E0. This one is your positron with the neutrino and with your neutrino. So you can say that from this beta decay, the electron, it do not exist inside the nucleus, or you may say that this electron may be produced during the radioactive disintegration. So basing on this theory, that is basing on this hypothesis, that is proton-neutron hypothesis, the elements can be classified further, that is known as, for suppose the isotope, let us take first the isotopes. What are the isotopes? The atoms having the same atomic number Z but different mass number A. Z is same but A is different. So in that case the atoms are called as the isotopes. So for example, if you will see, this is your, simply we denote, let me write it here, we denote an element. So this is your Z, X, A, X may be any atom. So this Z is your atomic number, this is your atomic number, and this represents the mass number. Okay, and this A is nothing but Z plus N, and here this N is the neutron number. This N represents the neutron and this Z represents basically the proton number. So this one is important. Okay, So now you can see here, in case of 1H1, so this is in the form of ZXA. This is in the form of ZXA. So this is 1H1 means proton, the number of proton is here 1, and the number of neutron, this will be equal to 0. Or simply now for this isotope case we should have Z same but different A. Now we can see that they all have Z same, that is 1 1 1, but they all have, this hydrogen all have the A, that is the mass number is different, that is 1 2 3. So these are called the isotopes of the hydrogen. So 1H1, 1S2 and 1S3, these are called the isotopes of the hydrogen. And similarly in case of the helium, you can see this Z value of helium, it is 2, but the mass number is here 3 4 6. So these are called the isotopes of the helium. Okay, now let us see for the isobars. So what are the isobars? The atoms having the same mass number but the different atomic number Z are called the isobars. So it means that if we will consider the lithium and the beryllium, so in this case the mass number is same, that is here is 7, here is 7, but here you can see the atomic number, that is 3 here and this is 4 here, they are different. And here also for the sodium and neon, these are your same, that is the mass number is same and the Z are different. So these are called the isobars. So in case of isotope, Z is same, A is different, but in case of isobar, this is just reverse of that, that is the mass number is same but atomic number is different. Now we will see isotones. Isotone, so this is your iso means same. Okay, iso, always the iso means same. So when they have same number of neutron, isotone means same number of neutron, then these are called the isotones. That is for chlorine 1737 and for potassium 1939. You can see the number of neutron here is 37. You know this 37 is nothing but A value. So you know A equal to Z plus N, and here Z value is 17. So 17 plus dash, that will gives you 37. So N will be equal to 37 minus 17. So you will get 20. Similarly for this K, this will be 39 minus 19. This is your A and this one is your Z. When A minus Z, so you know A equal to Z plus N. So the value of N will be equal to A minus Z. So this will be equal to 39 minus 19 also 20. So they all have the same number of neutrons. So we can say that these are called the isotones. Okay. Now let us see for the isomers. So in case of the isomers, they have the same atomic number, same mass number, but they will differ from each other in their energy states and they are called the isomers. So now in this case of the isomer, Z value is same and A value is same, but they will differ from each other in their energy state. So these are called isomer. So basically in case of isotope, just try to remember, in case of isotope, what are same? Z is same. Which one is different? Atomic mass number is different. In case of isobar, A value is same, Z value is different. And in case of isotone, which one is same? The number of neutron is same. And in case of isomer, the last one, in case of isomer, A is same, Z is same, but which one is different? The energy states are different. So these are the basic classification of the elements according to the proton-neutron hypothesis. Okay. So these are all about your constituents of the nucleus, how the nucleus is made up of. So after the conclusion, just a minute. So here we conclude that nucleus consists of the centrally positive charged nucleus. You can see that this is the proton and your neutron, and electrons are revolving around this nucleus. Okay. So electron carry the negative charge and the proton has the positive charge and the neutron has the neutral character, or you can say no charge. P for positive, so the proton has positive charge. Electron, you see the negative sign, this is your negative charge, and the neutron, N for neutron, N for no charge, or this is neutral in nature. Okay. So as a whole, just remember one thing, as a whole, since the number of proton equal to the number of electron in an atom, so we can say that the atom always in its neutral state, always it will be in its neutral state, that is it has no charge. Because if I will consider, suppose carbon atom, so it has 6C12, let me write. So in this case you see this is your atomic number or this is your proton number. Okay, so here in this case there are 6 number of protons and there are 6 number of electron. So 6 individual proton, they will carry the positive charge, so it has 6 positive charges. And electron also, in case of carbon there are 6 number of negative charges. So 6 positive charge, 6 negative charge, when they will combine, so as a whole they will form a neutral atom. Okay, so this is all about your constituent of the nucleus. This is all for today. Thank you all.